I showed an image of a jet fuel line refueling a jet tank in an airplane. And in the time that jet A or kerosene is flowing through that tube, more energy is being transferred into the tank of that plane than the largest nuclear power plant in the world produces.
Hi everyone, welcome to the Climate Confident podcast. My name is Tom Raftery, and with me on the show today, I have my special guest, Dan. Dan, welcome to the podcast. Would you like to introduce yourself?
Tom, such a pleasure. Thanks so much for the opportunity today. My name is Dan Sutton. I'm a co-founder and CEO of a company called Syntholene Energy, and we're in the business of making clean, drop-in substitutable synthetic fuels, specifically eSAF for consumer flight. And we're really excited to be building a new system that can allow us to produce this fuel in a new cost-competitive way.
Interesting. Looking forward to digging into that, Dan. But before we do, give us a short version. You've built before. Why did you decide to go after synthetic fuels for your next bet?
Really appreciate that opportunity. And we're in an incredible time in synthetic fuels. I'm really lucky to have joined Syntholene at a time where almost a decade worth of engineering work was done on our particular pathway. We call it a thermal hybrid production system, which allows us to use heat and electricity as dual inputs into our system. And I join a group of certified genius engineers who've really made this their life's work. My co-founder and chief engineer, John Kutch, has spent 30 years in the advanced energy business. He's designed a nuclear reactor. He's built waste to power plants, hydroelectric dams, all kinds of incredible infrastructure. And I think he cottoned on initially in the sort of early 2010s to mid 2010s that we've reached this technological advent where the contributing technologies to our supply chain have reached sufficient industrial maturity, durability, viability commercially, not just at a lab scale, where we really can imagine the synthesis of hydrocarbons, fuel molecules that are drop-in substitutable for the same engines, motors, and turbines that we use today, but in a carbon neutral way and for the first time in a cost competitive way. So John set out to make this his business. He built out some prototype infrastructure, some early stage engineering, and then collaborated substantially in the United States with the National Renewable Energy Lab and the Idaho National Lab, where some groundbreaking work happened through the sort of late 2010s and into the early 2020s. At INL, they built a system that showed this thermal integration pathway. It showed its ability to produce hydrogen, which is a really critical feedstock, sort of the defining cost factor of synthetic fuels. And they showed the pathway to be able to produce it radically cheaper than it's been produced as of yet. They brought me in after that engineering work had been performed to say, hey, you've got some experience building companies, you've got some experience raising funds and doing PR and being on podcasts like this. Let's go out and turn this great engineering project into a real company and celebrate that we get to go tell audiences like yours that this really does exist today. It's been demonstrated at a lab scale. It's time for us to go prove it out in the real world. And that's the business that Syntholene's actively in. So I'm really excited to be able to share that the days of low-cost synthetic fuel are in front of us. In our lifetimes, we will live to see the widespread adoption out of economic self-interest of these clean fuels. And we really believe they're going to be cost competitive and ultimately cheaper than fossil fuels reasonably within the next 5 to 10 years.
I've had people on the podcast before who are making SAF. One was doing it from waste, as in from kitchen waste, that kind of thing, waste oils. The other was doing it from waste fuels, like of bunker fuels from ships. What's your differentiator? How are you making this, not necessarily SAF, you call it eSAF, synthetic syntholene fuel?
Well, biofuels and recycled fuels are really interesting subject domains. I think the last 30 years of biofuel iteration have yielded some of the most compelling chemistry. It's incredible what they've been able to achieve, essentially starting with bio-based feedstocks and then refining them into viable liquid fuel replacements. There are some inherent limitations around biofuels, and I think it really comes back to feedstocks. Where are we going to get all of the corn and soybean oil and waste food oil that we need to be able to meaningfully substitute away from fossil fuels? And at some point in that equation, we often need to make a choice between food that goes on our plate versus food that goes into those supply chains. But nonetheless, we celebrate the biofuel producers. They've done incredible work. And in a lot of ways, we stand on their shoulders in how we imagine similar chemistries, albeit through a different process to produce the fuel. And similarly, recycled fuels, we should be recycling all the hydrocarbons we can. The molecules are incredible, and when we recycle plastic and refine it back down into something else, those molecules are just as good as the ones that we get out of the ground. What makes synthetic fuels or e-fuels unique is that instead of refining down from a crude input, such as fossil-based crude or bio-based crude or a recycled slurry that you then refine down, we actually synthesize the molecule from the ground up. So we start with its molecular components, hydrogen and carbon, and in fuel synthesis reactors, such as the Fischer-Tropsch reactor or the methanol-to-jet process, Fischer-Tropsch actually has almost 100 years of operating history. This is a very old technology that we understand really well. We can align those molecules into the exact carbon chains that we want, and we can actually target the output specific to the needs of our customers. So one thing that your audience probably is well aware of is the use of synthetic motor oil. Synthetic motor oil has a 60-year track record of delivering superior performance, better durability. It's a higher quality product to put into your engine that enhances your engine's operational life. It enhances your engine's durability, requires less replacements, and that's because of its molecular purity. Instead of using a crude input and refining down, they synthesize that motor oil from the ground up, and that leaves you with just the pure carbon chain. In this case, it's a shorter chain that has more lubricant capability than a fuel, but it is just what the engine needs and none of the residual adulterants that come from the refinement process. So we're very much doing the same thing from fuel. We're not the first ones to have done it. Synthetic fuel's also been around a long time. It's just never been both economic and clean.
And where are you sourcing your feedstocks from?
So this is where we get into the mind-blowing aspects of synthetic fuel. The feedstocks for synthetic fuel are ultimately water, carbon, and energy. The energy is a pretty critical component because if we get consistently available baseload energy, and then we use that energy efficiently, the first step is dissociating hydrogen from water by cracking it through the electrolysis process. And that cost of that hydrogen and that efficiency of producing that hydrogen really has a linear relationship with our ability to produce cost-competitive fuels. So in the case of Syntholene, we attack this problem from two sides. First of all, we really need base load power. So intermittent renewables have trouble keeping up with industrial demand for operational process. If we have a wind and solar offering that is just on sort of 25 or 30% of the time, then we need a huge amount of battery backup to be able to operate at industrial consistency. And we solve this problem by using geothermal power. We've been building a demonstration facility in Iceland. Incredible place to do business first and foremost. The Icelanders are a very industrious people. They've built a lot of amazing advanced energy infrastructure. I think they're the only electricity grid in the world that is 100% renewable powered and also 100% independent. They run a lot of their electricity demand through geothermal. They also have a fantastic hydroelectric grid. But the great thing about geothermal is once you get the well dug and the turbine spinning, it is consistently available, at least in Iceland. That baseload availability is really ideal for the industrial process needs that a fuel synthesis producer or other industrial producer would need. Now, the other thing that geothermal provides is heat. And heat is kind of our secret ingredient. Instead of operating traditional electrolysis processes that have been around a long time and operate generally at quite low temperatures, we use a relatively new piece of technology that's just sort of only recently reached industrial maturity and long-term bankability, and that's called a solid oxide electrolyzer cell. Now, even just with electricity, it operates about 40% more efficiently than a traditional electrolyzer process, but it also operates at high temperatures. And so we can introduce heat from the steam that comes out of a geothermal well and actually cheat the first 150 or 200 Celsius of that SOEC's operating temperature. This net reduces the amount of electricity that we need. And so even in regions like Iceland, where that energy is super abundant, we're also very judicious about how efficiently we make it. That heat and electricity goes into the SOEC. That lets us crack the hydrogen from the water, gives us our hydrogen, our first critical feedstock, and probably the lion's share of the expense of the end hydrocarbon chain molecule that we want to get to. And then we add in captured CO2. We really like biogenic CO2. We like point source captured CO2 from local industry. We keep a really close eye on direct air capture and, interestingly, direct ocean capture. So not as much on people's radars, but direct ocean capture is a great piece of tech. There's about 150 times the concentration of CO2 in the ocean, and the ocean acts as a carbon sink. So when we get that carbon efficiently, then we can add that into a fuel synthesis reactor and come out with these designer molecules that just give us the carbon chain that we want to be able to deliver clean, high performance, drop-in substitutable fuel to airline customers around Europe, around the UK, and around the world.
And why is this conversation more urgent now than it was even 3 years ago or right now, 3 months ago?
Well, it's pretty urgent right now because we are now really in a deep and painful understanding of the fragility of fossil fuel supply chains. Fossil fuel has a diversity of negative externalities. I think the listeners on your podcast are going to understand most of those externalities pretty well, but supply chain dependency is one that we don't talk about that often. Most of the fossil fuel reserves in the world are not exactly in easy, safe, democratic Western nations. And as such, I think we're having a real revelation about how likely are these supply chains to be interrupted because of political conflict, because of violence, because of changes in political dynamics globally. And as of the conflict in Iran, we're going to be seeing a new risk premium applied to fossil fuels that I don't think people were effectively pricing in before this conflict. If we look at the global fossil fuel reserves, the largest reserves in the world, maybe the top 40 or so nations, these are often politically conflicted places. They're not necessarily democracies. They don't necessarily share the same political beliefs and aspirations as the EU or the UK or the Western world generally. And so supply chain risk, political conflict risk, this is another externality of fossil fuels that I think we need to solve. And in the conversations we've been having with governments, with politicians, with stakeholders who are seeking increasing diversification of their energy grids, they want energy sovereignty. They want energy independence. And this is an incredible opportunity to remind us all that we need to detach our hydrocarbon fuel consumption from fossil fuel supply chains in any way we can. And the more that we can do that, the more that we can imagine the use of clean, carbon neutral hydrocarbons long after our fossil fuel reserves are exhausted.
And you're going after SAF in particular because the aviation industry is in trouble right now. I heard that Fatih Birol from the International Energy Agency said Europe has 6 weeks of aviation fuel left right now. But obviously, things are starting to change there. So hopefully that'll come back. And I think Europe anyway has better options than Asia when it comes to aviation fuel. But tell me about the aviation fuel industry and why you've particularly targeted that one.
So the immediate shocks to the price of jet fuel, which has tripled over the course of the last 6 weeks, are indicative of aviation fuel Jet A1 as kind of a canary in a coal mine. Whenever there are supply chain interruptions, kerosene or Jet A1, which is one of the smaller and more essential fractions that we get out of the fossil fuel refinement process, it often leads and has the most volatility and the most explosive impact on price. And that is an immediate shock. I think that prices will settle. I think that supply chains will stabilize. We really hope for an end to this conflict. I'm mindful of the human cost. And so prices up, down, sideways, we're going to see a lot more explosive volatility in jet fuel generally. But jet fuel is interesting because fueling airplanes is one of the most difficult to abate sectors. Ultimately, if we want to reduce emissions from aviation travel, which I think is a priority in many governments across the world, that's true in the US, it's true in Canada, it's true in the EU and the UK. There's mandates and requirements and subsidies all through those European regions, and also in Asia. There's probably 4 or 5 nations that have said, we recognize that aviation has a disproportionate impact on emissions, not just CO2 emissions, but also other things like copper and cadmium and lead, greenhouse gases like nitrogen oxides and sulfur oxides. And these things do have a disproportionate greenhouse gas effect, even more so than CO2. The problem with aviation is it's really hard to do it without jet fuel. Hydrocarbons are incredibly energy dense. There's really nothing else like them. In fact, I presented at a conference yesterday and I showed an image of a jet fuel line refueling a jet tank in an airplane. And in the time that jet A or kerosene is flowing through that tube, more energy is being transferred into the tank of that plane than the largest nuclear power plant in the world produces. So that just gives you an idea of how uniquely energy dense hydrocarbons and jet fuel specifically is. And so we can't really imagine with our current understanding of physics how to electrify a jet turbine. If people want to fly across the Atlantic Ocean in a matter of hours and not a matter of days, we do need to use some energy dense fuel. There's been conversations about the potential to use hydrogen. That hasn't really played out practically. And so we're sort of stuck with hydrocarbon fuels. And aviation's also interesting because very few people participate in it. Despite the fact that maybe 6-7 billion people in the world have never flown on a plane, it probably contributes about 4% of total global CO2 emissions. And that's just CO2, not those other things that I was talking about. So the opportunity to decarbonize aviation has become a massive political priority. We see it in the EU, we see it in the UK. This isn't a nice to have. This is something that we're going to have to address. We might as well address it sooner rather than later. And I think it's one of the reasons why I'm so excited about Syntholene and our capability to produce increasingly cost competitive eSAF, because all of a sudden now we don't have to ask for these massive economically destabilizing green premiums. We can say, hey, there actually is a pathway to get this stuff cost competitively with fossil fuels. And that's absolutely the mission that we're dedicated to at Syntholene.
Okay, interesting. So talk to me a bit about that, because synthetic fuels are going nowhere if they can't be cost competitive. So just how cost competitive do you expect Syntholene to be?
I think you're absolutely right. And I think oftentimes in our excitement around new technologies, the unit costs can kind of get left to the side. There's been some incredible breakthroughs on the chemistry of fuel synthesis and a lot of companies that have built a lot of excitement, peer firms in the eSAF business. And those companies generally haven't been able to address costs or projections of future commercial costs that are below sort of 5 or 6 times the price of fossil fuels. Oftentimes, they're about 10 times the price of fossil fuels. Now, governments have stepped up. There's mandates for consumption, there's subsidies, there's policy measures to help try to build a bridge from those really high cost points today to hopefully the breakthroughs, technological breakthroughs and economies of scale that will bring those costs down. But my view is that the use of intermittent renewables to low temperature electrolysis, as we discussed before, it's just fundamentally thermodynamically inefficient. It's running up against a physics problem. And when the physics problems persist, it's just really hard to imagine it ever getting to cost competition with fossil fuels, even with many, many billions, tens of billions of dollars worth of economies of scale. What makes Syntholene unique is our ability to use this thermal hybrid process, heat and electricity, into high temperature electrolysis devices. These high temperature electrolysis devices, SOECs, are really well understood now. They were kind of science experiments in the early 2010s. They started to reach commercial viability in the mid 2010s. Now their durabilities have increased like 300x just over the course of the last 46 months. They're way more industrially bankable. They're viable. They have supply chains that can produce them in many, many megawatts worth of scale. And so now really is the technological advent of being able to use that. And it is this ability to use heat and baseload electricity. The electricity certainly needs to be low cost. So we have to target regions like Iceland where they have a great industrial electricity base and also an untold abundance of many, many megawatts, perhaps gigawatts, perhaps tens of gigawatts of known but unused and otherwise stranded geothermal assets. And that is really the key to our ability to approach cost competition with fossil fuels at a reasonable industrial scale. We don't need to have, $50 billion worth of refinement infrastructure to be able to produce at that cost. In fact, our first commercial footprint, which is projected to produce around 20,000 tons per year, sort of 25 million liters a year, we believe we're going to be able to get to about $1.25 US per liter factory gate production cost. And that's comparable to most of our peers. I've analyzed a lot of the peers in the industry, and they sort of start around $6 to $8 per liter. So I think it's really nothing short of a groundbreaking advancement in the efficiencies and the cost profile. And at least it gives us a pathway to say there's a bit of a premium over the 10-year moving average of fossil kerosene prices. Right now, it would be cheaper than fossil kerosene prices, but I don't think we can anticipate these costs to persist. But it does solve that externality of political volatility. It does solve the externality of feedstock volatility. Be mindful, we just use heat, water, carbon. So as long as we can get those prices in a stable way, we can actually offer our consumers a predictable price instead of having to hedge and bank and hope that we're going to have stable, fossil fuel inputs coming through to Europe. And so I think this really is the first time to chart a path where synthetic hydrocarbon kerosene can ultimately be cost competitive with fossil fuels and perhaps even lower cost than fossil fuels have been over the last 10 years.
Okay, what's the market for SAF for the next 10 years, and how much of that market do you anticipate Syntholene being able to target?
Oh man, I wish we could take a swing at a big market share, but the market for aviation fuel is massive. This is also notwithstanding marine shipping fuel, which also has global emissions reductions mandates coming in. And that's probably about 500 billion a year in the next 10 years. We're all really excited about electric cars. I've got one in my driveway, but the global gasoline market is still 2.5 trillion. So there's a lot of demand for fossil fuels. The aviation industry specifically is probably about 350 billion this year, and demand for aviation continues to grow really radically, in fact. It's feasible that the demand for that fuel could grow about 3x by 2050, and this is because so many people have never been on an airplane and they really want to be. So even through COVID, we saw a bit of a dent in aviation fuel demand, and then it got right back onto its growth trajectory. And so this isn't going away from a consumer reduction perspective. There's a lot of people that want to be in airplanes and taking airplanes. And so SAF specifically, partly, enhanced by mandates and enhanced by policy measures that are encouraging the use of this cleaner fuel, it looks like that demand is going to be probably in the 5 to 10 billion range for eSAF specifically, come around 2030. And then by 2035, those mandates expand, and that could look more like about 20 billion a year. Syntholene doesn't quite have a vision yet on how we're going to supply all of it, but we do have our first commercial footprint, which has been designed. We're deploying a demonstration facility right now and hope to expand to about 20,000, 25,000 tons per year of production reasonably before 2030 if we play our cards right and get to the ever elusive final investment decisions, which have sort of been a bit of a struggle for the rest of the industry. I think that's largely a function of unit economics. But should we get that right and demonstrate that we can produce this fuel cost efficiently, even at a small footprint, it's my view that that footprint can be profitable. It can be profitable on a project level. It can be profitable on a company level. And because of its engineering oriented around modular, scalable, small increments coupled together, then we really do have a vision on how to capture those economies of scale. And I hope that Iceland alone is producing many, many billions of liters of this fuel over the next 10 years. And I think Syntholene has the technology to do it.
So you're basing your production very much on the geothermal and baseload renewable energy that's available in Iceland. Does that mean you are completely tied to Iceland, or are there other regions and geos with similar access to renewable energy and geothermal, which, as you say, you need to produce the Syntholene at the cost that you're getting it today?
First of all, we love Iceland. Iceland is an incredible place. It has incredible people. The fact that they came up there in, I think, originally the 8th century and then again in the 11th century and were able to create a civilization and society that's relatively small but incredibly industrious, all the way from machinists and tool and die makers. I think they have 12 ports that can handle large draft ships. They have 3 airports. I love my time in Iceland, and I love the industrious and solutions-oriented nature of the people. They also have an exceptional endowment of geothermal, really hard to wrap our arms around. Our friends at the Clean Air Task Force, who are sort of specialists in this new grade of geothermal called super hot rock. Super hot rock refers to geothermal resources that can be tapped above 300 degrees Celsius. That's really significant because it allows far more efficient electricity generation and far more concentrated energy densities in like single boreholes. I think that they imagine that there will be a 50 megawatt single well that they can produce in Iceland over the course of the next 10 years. And this is energy that's been around for 100 million years. It'll be around for 100 million more. Clean Air Task Force projects that if we could just tap 1% of Iceland's total known super hot rock availability, we'd be able to produce the energy equivalent of about 2 billion barrels of oil per year. That's like 5 million barrels a day. It's about 5 or 10% of the world's total demand for oil and gas. Mm-hmm. So really hard to overstate the importance of Iceland in the future of geothermal. There's a lot of amazing tests that go on there, a lot of amazing breakthroughs that happen. The government is super oriented to expanding its geothermal business. And they also have, I think, a distinct advantage in the political landscape. So a case study here is that Syntholene applied for permits for our demonstration facility construction. Those permits took about a week to be able to get us, the green light to go out and build this stuff. In fairness, we'd done a lot of ground game and we'd prepared a lot to be able to get a really good shot with great engineers and EPCs to make that permit really obvious and easy to issue. But such a permit could have taken years in the European Union, in Canada, and the United States, years easily. So this is a country that has great energy access, but also appreciates the importance of encouraging foreign investment. Now, when we imagine scoping beyond Iceland, I think we can make many billions of liters, many millions of barrels a day in Iceland. And it won't just be Syntholene. There'll be other people doing that as well. But there are other geothermal regions around the world which do have this special super hot rock access. We don't need it to be quite 300 Celsius. Syntholene would be really happy with 150 to 200, maybe 250. And we see endowments that are relatively shallow, relatively accessible. They've got the right geologies in places like Nevada and Utah, in places like Alaska, places like Indonesia. Italy has some incredible volcanic action. We all remember Mount Vesuvius. And so there are other regions in the world where we could set up these like concentrated, centralized, adjacent to geothermal resources. But I think where it gets really exciting is as we see the advent of more and more adoption of very high temperature Generation 4 small modular nuclear reactors. This is actually where a lot of my team cut their teeth and built incredible value over their 20, 30-year careers in the nuclear business. And these new reactors are interesting because they don't just produce electricity efficiently, they also operate at exceptionally high temperatures, which make them great candidates for industrial process use steam, super high temperature steam, sometimes 600 degrees Celsius. And that allows them to be a practical energy input for things like steel manufacture, cement manufacture, chemical synthesis, and yes, fuel synthesis. And so these SMRs, we've known about them for a while, for 2 or 3 decades. They're just starting to get to first criticalities. I think there's one operating in China. There's a couple more that are going to turn the lights on in the United States. And if we imagine a world where we see more decentralized small modular reactors and small modular arrays getting deployed worldwide, they are an excellent candidate for the kind of industrial process heat that fuel synthesis supply chains like our thermally integrated pathway require.
Okay, and the demo plant that you're putting together in Iceland, what does that plant need to prove for the story to become credible?
It needs to prove that the kinds of results that we saw at the Idaho National Lab in that groundbreaking thermal hybrid to SOEC work can be replicated. We don't actually need to replicate them perfectly. We just need to get in the range. If we're in the ballpark, plus 20%, 30% efficiencies, that really will be a groundbreaking moment for the production of synthetic fuels. Hydrogen is the core feedstock. That's the core cost driver. Can we get the right price of energy, and can we use that energy judiciously and efficiently? But if you ask my engineers, they think they might just outperform those lab tests. The technology's iterated a little bit since then. So we're really hoping to be able to demonstrate the effective thermal integration of geothermal steam to the kind of industrial process steam input that we need to operate the SOEC. Then we want to validate the efficiency of how well that steam and the electricity use gets utilized. And then we want to validate the scalability. Can the modules that we've built in this relatively small demonstration exercise scale up? Can we have multiples, twinned units, 5 units, 10 units, 50 units over time that can do the same thing? And I think it's going to be a watershed moment for the synthetic fuel business if we're successful in demonstrating this effectively.
And what would you say this space needs most now? Is it better technology, cheaper energy, policy certainty, project finance, something else, all of the above?
The technology, in my view, is sufficiently mature. We get to live in this era where the technology has come to the point where we really can imagine this pathway to cost competition with fossil fuels. That's not to say the technology is not getting better. The SOEC designs are just sort of early in their efficiency curves, and I think we are going to see great SOEC developers continue to iterate, continue to achieve novel efficiencies, and we're really excited to be along for that ride. We don't build SOECs, we partner with the best in the world who do the SOEC work, and they are very excited about the future of their own technological progression over the next 10 years. I think co-locating fuel synthesis infrastructure with low cost and baseload available energy is really important to this equation. That's key to our thesis. We're seeing other firms kind of cotton on to that reality. The policy measures are great. We do see a bit of a gap between the policy work that's been done to encourage the consumption of this fuel and projects' lack of ability to get to final investment decisions. And ultimately, upon discussion with industrial investors, large project financiers, banks, oil and gas companies, of which we've canvassed the lot. We really want to get the take on why are so many of these projects struggling to get to those final investment decisions. The answer does come back to unit economics. We need to get at least a bit of a premium, not a 10x multiple premium, not a 5x multiple premium, a tolerable premium that then charts the pathway to be able to produce these fuels cost competitively so that we're not forever reliant on subsidy. Subsidy is a bridge measure, mandates as a bridge measure. These are incredibly important. We've seen them work in a lot of other industries, solar, electric vehicles, diversity of advanced energy infrastructure that needs a bit of a boost to get going and start capturing some market share. But we do need to understand how they eventually become competitive toe-to-toe with fossil-based hydrocarbons. And that's no easy challenge. Our world has had 150 years of quite ridiculous abundance of these hydrocarbons from fossil, and they really do underpin a lot of the technologies and amenities and luxuries of our society. And so I think that that unit economics piece, when firms like Syntholene get that right, it could very well open the floodgates for scaled investment into cost-competitive synthetic fuels for use in aviation, eventually for use in marine shipping, and for all other uses of petroleum-based liquid fuel products that we use in our society today.
If this works, what does success look like in 5 or 10 years? What changes in the real world?
Imagine going to the gas station and instead of regular premium and ultra premium, you have regular premium, ultra premium, and then synthetic. And synthetic or synthetic blend can actually still be cost competitive. That would be amazing at airports. It would be amazing for marine shipping. And I think the coolest thing is that you probably won't even really notice. Like if we get our job right, consumer behavior won't change. Consumer behavior will still go to their same pumps. They'll still fly on their same planes. They'll still fly the same tickets. This is a drop-in substitutable fuel. We make the same fuel, albeit a molecularly pure version. And I think success looks like a pathway to imagining long-term use of carbon neutral, low externality, politically decoupled from fossil supply chains, hydrocarbons. And this is something that I think, especially in green energy audiences, can be a little shocking. It can be a little contentious. It certainly was for me. But I believe that I want a world where we can continue to use hydrocarbon fuels in perpetuity. We don't rely on fossil feedstocks that are coming from reserves that are at least getting more expensive to pull out of the ground. Eventually those reserves get really expensive, economically non-feasible, and eventually they run out. Maybe that doesn't happen in the next 20 years, but we could imagine it being at least economically impactful in our lifetimes. And I think that civilization baked in with fossil fuel, or I should say hydrocarbon fuel consumption for hundreds of years would be an amazing and achievable outcome, using the CO2 that we've emitted into the atmosphere that's sunk into the ocean as a battery. That CO2 has value. That CO2 can be extracted economically self-interestedly and used as a feedstock for fuel. And that's the kind of future that I want to live in, and it's the kind of future that my team and I want to build.
Now it's time for the lightning round, Dan. So I have a few questions for you in this, but single one-sentence answers. You up for it?
Let's go.
Okay. First one. If you had to choose today, would you prioritize cheaper fuel or cleaner fuel first?
I would prioritize cleaner fuel, knowing that we can get that cleaner fuel cost competitive over time.
And if you had to scale this business, would you build closer to demand or closer to cheap energy?
Closer to cheap energy, 100%. We're really good at moving hydrocarbons around the world. We've got tankers, we've got pipelines, we've been building them for 150 years. We should continue to utilize them.
As long as they're not going through any straits.
Let's minimize the politically conflicted straits.
Outside of aviation, where do you think synthetic fuel makes the strongest case first?
Outside of aviation, I think we're going to see huge clean fuel demand in marine shipping. That's all coming. There's global mandates. It's not government specific. And the shipping industry is actively taking a very close look at synthetic fuels and other forms of lower emissions capabilities to generate power to run their ships.
What is one myth about climate or clean fuels that this industry still tells itself?
It's forever got to be more expensive. We do not need to sacrifice economic self-interest to make these fuels a widespread contributor to our petroleum-based supply chains today. This technology exists today. It's going to happen. I think it's going to happen within the next 10 years.
In the end, do mandates matter more or do economics matter more?
Mandates are a great tool to encourage the proliferation of production infrastructure, but they're only useful if they lead to the economies of scale that get us to economic competition.
What could kill momentum in this market faster than most people realize?
Inverse oil shocks, a price bottoming out in the cost of kerosene. If we saw kerosene dirt cheap, then that widens the spread between the premium that people pay for these alternative fuels.
Left field question for you now, Dan. If you could have any person or character alive or dead, real or fictional, as a champion for Syntholene, who would it be and why?
John D. Rockefeller. And I'll tell you why. Because Standard Oil's brand promise in the 1890s was to produce the highest quality fuel at the lowest possible price. He never could have imagined that that fuel would be produced synthetically, but if he understood the technology roadmap of where we are today, he's the kind of guy that would have had the long-term vision to say, this is the future, we've got to invest in it. He probably would say we need to own it all and we need to monopolize it. We need to own all the distribution points too. So not a perfect character, but the highest quality fuel at the lowest possible price, that is what allows any commodity, even a specialty commodity, to win.
Okay. Dan, we're coming towards the end of the podcast now. Is there any question that I didn't ask that you wish I did, or any aspect of this we didn't touch on that you think it's important for people to be aware of?
My whole life, I've been taught that fossil fuels are morally wrong. They're inherently evil. They are untenable in the long-term energy mix of our civilization. And I would challenge your audience to consider that if the environmental externalities, the supply chain externalities, the conflict externalities could be solved, fairly enough, a pretty broad assumption, but if they could be solved, what would a world of 1,000 years of hydrocarbon abundance look like? What would your life look like if you could use 10 times the amount of hydrocarbons that you use today? What would life look like in sub-Saharan Africa? What would life look like in South America? What would life look like around the world, beyond the world, to the moon, to Mars and beyond, if we had access to clean, cheap, unlimitedly scalable hydrocarbon fuels? And that is the core North Star of why Syntholene exists and why we get up every day and attack this problem set.
Dan, if people would like to know more about yourself or any of the things we discussed on the podcast today, where would you have me direct them?
You can check us out at syntholene.com. I'm on Twitter, D Sutton, SUTTON 1986. Hit me up. Check me out. I'm on LinkedIn. I answer my messages. I'd love to talk to you. I'd love to talk to your audience. And let's go. The time is now to build clean, high performance, low externality synthetic fuels. And we'd love you to join us on that mission.
Fantastic. Dan, that's been really interesting. Thanks a million for coming on the podcast today.
Thanks so much for your time.